Well, this is the electrostatic deflection of electrons lab, and depending on which lab you did first, if you've done the electric fields lab, of course electric fields are vectors and they have a symbol E that represents them, and we're not going to go through the electric field story here. We'll do that either next week or you've already done that. So we know that if we put a charge in an electric field, it experiences an electric force. This is sort of a counterpart to, as I explained in the field mapping experiment, a counterpart to this equation that we talked about last semester. That is the gravitational force, which is called weight, is equal to m times g. And this is a similar setup, which we explain, or we will explain next week when you do the experiment, if you haven't done that one. So here we have an electron tube, and the charges we're talking about are the charge on the electron, which is minus 1.6 times 10 to the minus 19 coulombs. And again, we don't put the minus signs, we don't build in minus signs. Ben Franklin kind of stuck us with the minus sign for an electron, and so that's its charge. So let me draw a sketch, which is figure 1 in your handout, cathode ray tube. Looks something like this. Back here is a filament that's just a little, the thickness of a hair, a fine piece of wire that we heat up orange hot, and you'll see that when you turn the apparatus on, you'll see an orange glow coming out of the back of the tube, which is a bunch of electrons being boiled off and liberated from the metal, and then they're going to be excited or attracted by, there's a force on a charge in an electric field. They're going to be attracted to a section here that looks something like that, a little metal cylinder, and the electrons, which are in a cloud around the filament, they'll be attracted to this positive charge. It's going to be a positive charge, and they're going to head over to that anode. It's an anode, and it's hollow. So at a distance, they see this positive charge, and they're attracted to it, accelerated rather vigorously. In fact, in this little distance, maybe it's a 1 or 2, well, it's less than a centimeter, the electrons are going from 0 to a good fraction of the speed of light, which is 300 million meters per second, in just that distance. Much better than the average Tesla car. In any case, so they're easy to accelerate because they're so small and so light, and they have a very strong negative charge. So when they get to that, when they get that cylinder, they see that it's hollow, and they've got all the speed. They just keep going right through it, and then there's going to be another cylinder like this, which is at an even higher positive charge, and they'll be accelerated twice. So the two accelerating voltages, this in your lab when you look at the equipment, this is called the C minus and that's called the B plus. That's really irrelevant, but it's two accelerating voltages together. If you add these two voltages, you have V sub 2, the total accelerating voltage for the electrons. And when they come out here, they're going to be going really fast, and they're going to be heading towards the front of the tube. Okay, so the first thing they encounter is a set of deflection plates, and this is a top view. So the first set of deflection plates that they run across is the vertical deflection plate. So I just will draw them in like this, and they're sitting like this. They deflect the electrons vertically, which is why they're called vertical deflection plates. The next set of plates, looking at again from the top, looks like this. So here's these electrons coming through. They're going very, very fast, pretty close to the speed of light, actually. And they're coming into this set of plates that are, they're horizontal deflection plates, which means they're set up vertically so that when the electrons come through them, they're attracted either to one plate or the other. So if this plate's positive and this plate's negative, they'll be attracted to the positive plate and repelled from the negative plate. Like charges repel and unlike charges attract. We have already seen that. So they're going to go through this they're going through these deflection plates, and they will be deflected, which basically means they're going to go something like that. Okay, and so let me just draw the center line of that tube and draw this angle here. We'll call that angle theta. That's the deflecting angle. Okay, and we need to know that angle, and you're given the distance between the middle of these deflection plates and the screen. It's unfortunately 4 and 21 32 of an inch. 4 and 5/8 of an inch roughly. So you need to know this distance, and that distance is called z. I'm going to call this the z-axis this way. So the z-axis is this way, the x-axis is this way, and the y-axis is this way. So this is the distance that you'll be needing, and it's in the write-up for you to use. So this distance here is called big D, and it's the distance that the beam is deflected from the center of the tube. Now this tube has a grid on it, and this grid is in 1/4 inch segments, and the tube is, this grid is 2 inches by 2 inches. So your center is in the middle, so that the electrons can be deflected an inch to the left, an inch to the right, inch and up, inch down. We're only going to deflect them with the horizontal deflection plates horizontally, so they're going to move from +1 inch to -1 inch. Unfortunately, it's in inches. But this is in inches here, and this is in inches here, and so if you want to know the angle, that tangent of that angle, of course, is the opposite over the adjacent, which is d over z. And since they're both in inches, you can get away with it. Just use inches over inches, and the units cancel out because tangent theta is a unitless radian measurement. So we're going to need to know the tangent of the deflecting angle. That's this angle here, starting pretty much from the middle of those plates. And the plates, by the way, are flared out so that the electrons actually deflected more vigorously here. They're deflected more like this, and then the deflection occurs right there. It doesn't occur in this slope like this, so that you have to bend these plates out of the way, otherwise the electron beam is going to hit the plate instead of going over to the screen. So they're flared out, which is a bit of a problem, which we have to cope with a little bit later. Okay, so that's the process. We have a bunch of electrons. They're accelerated in 2 stages, V sub 2, and they're deflected by a deflecting voltage, V sub D, which is a horizontal deflecting voltage. And that's done with one power supply with 2 voltages and a separate power supply with a deflecting voltage, which we'll go over when we take a look at the apparatus. So we're going to need to know this, we're going to need to know this. And we want to relate these things to the tangent of that angle, because that's where it's deflected from on the screen. So that's the general setup. It's fairly complicated, a lot of electronic things going on here, but what our goal is to figure out what the horizontal deflection plates look like. Now we can't break into this tube. There's a vacuum in this tube, and so we can't get in there to take a look at it. In fact, the tube is coated with a coating so that the electrons can go around and around and around, and so we can't even see inside that tube and look at the deflection plates. So we're just going to have to model them. And we're going to have to model them like 2 parallel plates, because it's much simpler to do this. Now, if you've done the electric field lab last week, then you kind of know what I'm talking about here. This is one of the patterns that you studied last week, and one line is positively charged and the other line is negatively charged, and there is set up in here an electric field, making the electrons go repelled from the minus charge and attracted towards the positive charge. So if you've done that lab last week, you know all about electric fields. You can draw pictures of them. That's basically our plan. If you look at the write-up, there's a whole lot of derivations. I would urge you to kind of see if you can work through those, see if you can understand where they came from. They're basically equations of motion for electrons. And there's nothing terribly new in that regard. So electron energy and so forth. So take a look at that. It should bring back fond memories of last semester in terms of energy and equations of motion. Let's just sort of stay practical here. What's the job here? The job is to figure out where are these electrons on the screen. So when the electrons get to the screen, there's a phosphor coating on the inside of the screen that when the electrons, if they have enough energy, if they have, we call it more than 200 electron volts of energy, then when they hit the screen, they're going to light it up with a phosphor, which is a green phosphor. So there'll be a dot there on the screen for where the electrons are. And we'll talk more specifically about how to make a nice looking dot with your controls on the power supplies over here. So the goal of the game is to take this screen, and it's got 9 lines vertically, 9 lines horizontally, and put the dot here and here and here and here and here and here. There's 9 vertical lines, so we need to adjust this voltage V sub D till the dot moves over and sits on one of those vertical lines from +1 inch to -1 inch. So that's our data. 9 data points. What is the voltage V sub D that it takes to move the dot from the middle of the screen to 1 +1 and -1 inches? And I've got things to say about that when we look at the apparatus and how to do that. This tangent of this angle that we talked about over there is given by the following expression, which is derived with some difficulty, and this is what it looks like. Tangent of that angle, which you can measure by knowing this distance and this distance. There's actually only 4 different angles. Distance over here is 1/4, 1/2, 3/4, and 1 inch, either plus or minus, so it's the same angle. So there's 4 angles that 4 values for this tangent of this angle, and you have to figure those out. It's the angle whose tangent is 1/4 over this number, 1/2 over this number, 3/4 over this number, and 1 inch over this number. Those are all pretty small angles. So we can figure out the tangent of the angle. There's only 4 options here. We know the we know the deflecting voltage that puts the dot on each one of those lines, and we know the accelerating voltage, which we set over here. So the process is to set the accelerating voltage and then move the dot across the screen from +1 inch to -1 inch, and then change the accelerating voltage and do it over again. So we're going to do 4 runs, and we're going to get 9 data points of where is the dot on the screen from 0 to +1 and then over to -1 in 1/4 inch increments. So this value here, L over D, is the length of these plates divided by the distance between them. And because we can't really tell what they look like, we're going to have to assume they're just 2 parallel plates, because L over D is just one value. It's the length divided by we're assuming constant distance, separation distance between the plates. So this is what we're looking for. So if we solve this equation for L over D, we get 2 V sub 2 times tangent theta over V sub D. So this is the equation that we are going to end up solving, this being the length divided by the width, by the assumed to be 1 width of the deflection plates. That's the best we can do to figure out what they look like. We can't worry about the flared part because we don't know what it looks like exactly, although the manufacturer on page 4 of your handout, the manufacturer shows that this is the way they tried to build that. We don't know if they succeeded very well, but that's the way they tried to build that. So we need to measure V sub 2 and V sub D, these 2 accelerating voltages added together. V sub D, the voltage to deflect it across the screen from +1 inch to -1 inch. So we're going to get 9 data points And we're going to do this for 4 different accelerating voltages of around 200 total, 300, 400, and 500 around those values. And so we'll have 36 data points. And what we need to do then, let me just write out this table, which is table 1 in your handout. This is data I take off the screen here. And you will find, and I'll talk about that when we look at the apparatus, you find that when you turn the apparatus on, your dot is not going to be right here. It's not going to be at 0, 0, which it should be theoretically. All these equations in the handout are based on the dot being at 0, 0 when you turn it on. But that's not going to happen. The dot's going to be over here someplace. It's going to have a y component and an x component. And we're not worried about the y component. We're worried about only the x direction. So on the tube that I was looking at just a bit ago, that you will look at shortly in the handout, in the lab, the dot is over here someplace. So that's a little bit confusing. So we have to have this table. We're going to list, these are the values for d, that is the distance along the tube face. And you're going to put your values for V sub d here. Okay, so when you turn the tube on, the dot's going to be there. So it's not on a line, and so you're going to need to apply a voltage. If you apply a voltage to move that dot to the right, we're going to call it a positive voltage. If you apply a voltage to move the dot to the left, we're going to call it a negative voltage. This is like the x-axis here. So it's going to take some voltage to move this dot over to this line, and it's already below 0, so to speak. And so you're going to get some numbers like this. Let's see, say 3 volts to put it over to this line, and it's going to take 8 volts to put it over on that line, and it's going to take 13 volts to put it on that line, and 18 volts to put it on that line, and 24 volts to put it on that line, for instance, and maybe 30 volts to put it over here. So, but the dot is here. So this is actually positive, even though it's below the 0 here, because it takes some voltage to move it over to this line, and that's that way, which is called a positive voltage. So this voltage here might be 6 volts, and this might be 12 volts, and this might be 15 volts, whatever. Those will be minus because I have to make the dot move this way, which means the voltage is going to be minus, and I'll show you how to do that in the on the apparatus. You simply need to pull a plug out and turn it around. That this plate, which was plus, is now minus. This plate, which was minus, is now plus. Just move the dots the other way. So I'm just making up the data, which is something like the data that we will take a look at from the tube. So what you need to do then is subtract 8 volts from all these numbers to make this 0, because this then models a tube that's perfect, and when you turn it on, the dot's there instead of there, because that's the way these equations are based. So if you do the subtraction here, you get 5 here, you get 10 here, you get 16 here, and so forth. And over here, you get minus 5. 8 from 3 is minus 5. 8 from minus 6 is minus 14. So when you do this adjusting, you should see that the numbers here pretty much correspond to the numbers on each side are pretty much the same, except for the plus or minus sign. And I'm just making these up, so I've not made them up very nicely. So what you need to do then is to average these numbers, forget about the sign, and that gives you the deflecting voltage to move it to 1/4, 1/2, 3/4, and 1 inch. We know how to measure the tangent of the angle. That's easy. It's always this number divided into 1/4 and 1/2 and so forth. V sub d and V sub 2 work together to give you the deflection, and we're looking for the length to separation distance ratio for this. And it turns out that if you do the manufacturer's calculation of that average distance, it's going to be about 4. In other words, they're 4 times longer than they are far apart. We don't know what they look like. We can't look into the tube. This is the way they're supposedly built, but this is the way we have to model them. So, and again, the error analysis here is all based on your readings from the meters, and we will talk about the error analysis when we show this particular example setup after we make this discussion. So you're going to get you have nine data points here, but these data points should all be the same except for the sign on one side or the other. So actually you have 4 separate values. The value that move it, your adjusted value to move it plus a quarter or minus a quarter inch, plus a half, minus a half, plus 3/4, minus 3/4, plus 1 and minus 1. So you're going to get 4 data points, and you have 4 runs of 200, 300, 400, 500 voltages total for V sub 2. So you're going to get 16 data points. You're going to get 16 values using this formula 16 times to get L over D. So since we have 16 values, you can apply a more sophisticated analysis such as the standard deviation analysis to get the average value of the length to width separation for these plates and see how they effectively act. So that's the goal of the game. We'll never see what they actually look like. We will see how they kind of act. And since every tube is different, and these tubes are all built differently, if you turn on one tube, the dot may be here. You turn on another tube, the dot may be there. You turn on a third tube, the dot may be here. They're all built very differently, so we can't really know the right answer. We are going to get the right answer. So if you add up your errors, such as we'll talk about, of reading the meters, typically, you will get a certain percentage, and all you can do then is say that my L over D ratio, which is probably going to be somewhere around 4, ballpark of 4, 3.7, 4.2, whatever it is accurate to within, in the example that we will talk about in the lab, accurate to 3%. That was my error analysis for the total reading of the 2 deflecting voltages plus the two accelerating voltage plus the deflecting voltage errors. So that's the experiment. It's very involved and very confused. There's a lot of electronic stuff going on that you certainly don't know about yet. And but the goal of the game is to get a model for the value for the length divided by the width of these deflection plates, their effective length to width ratio. And it's going to be in the ballpark of 4. It's going to be different for all the different tubes, so there's no right answer. There's a right answer for each tube, which is different. That's it.